Hey everybody, this is the first video I've made in a while because I've moved out of engineering education into environmental research, where I provide engineering services to people who are doing environmental research. So I want to do a series of videos on some of the scientists I work with. So this is Professor Alan Cooper, who is very good at eDNA, or environmental DNA. Can you tell us a bit about that?
Sure. Environmental DNA is basically what is shed by organisms living in an environment naturally. You know, bits of skin, feces, urine, bits of hair, all that kind of stuff. Just think about while you're sitting or standing where you are, there's a big pool of your DNA around you. And what we're doing is using that DNA signal you leave behind, kind of like a forensics crime scene, to investigate biodiversity, things that are hiding in the environment you can't normally see, and also to go back in time and try and use the same techniques from the DNA which has been left at the scene of the crime or in the river to look and see how biodiversity is changing.
So I first heard of this during COVID when we were testing wastewater.
Exactly, yep.
So that could tell us that there was COVID in the town?
Yeah, it was brilliant. It worked really well because COVID's a virus and viral RNA can be quite a bit more difficult to work with and doesn't survive as long as DNA, the normal genetic material that we're used to dealing with. But it works so well in the COVID outbreak to track exactly which town was having an outbreak and what strains were involved there, that I was thinking, well, why don't we do that for all diseases, right? So, you know, measles, Ebola, should that ever turn up. You know, technically, the water supply, the water distribution and the wastewater treatment, if you surveyed that constantly, imagine monitoring that every fortnight for every decent-sized town across Australia. We've developed genetic techniques that can screen for all public health notifiable diseases. There's a list in Australia of things which you have to notify the government about when you detect, and that works for public health diseases. There's a similar list for biosecurity species, you know, fire ants or varroa mite used to be. You have to tell people when you find it. We designed one genetic test that would survey all of those things at once because we know the genetic targets we're after. And we designed it so that you could put it into the water distribution systems or the wastewater treatment plants and actually monitor everything which is going on in the area.
So let's come back, let's go to our diagram here.
Yes.
Where we've got a wastewater treatment plant.
Yep, exactly.
What does your sampling system look like?
Well, actually, here it is here. So it's very simple. It's a Dacron, nylon type filter, and it's pretty much like 1970s carpet. You know, if you go to a city council hall in those days, that thick weave carpet.
Yep.
That's exactly what it is. It's used in fish tanks to filter out particulates to get your water clean in your fish tank. And what we do is we put it inside, this is a wiffle ball, which is an American backyard baseball thing with big holes in it so you don't hit it over to the neighbours. And so what we did is just put the sponge inside the wiffle ball to protect the sponge from mechanical damage or being eaten by a dog, although the ball might actually increase that. Tie that down with a fishing weight and then throw it in the river and leave it there for 2-3 days. And this is all the DNA floating down that river, you know, coming out of the wastewater treatment plant or whatever. And as it's going through the filter's trapping and collecting that material. We come along and then grab that, it could be 2 days, 3 days, which is really useful because it's at night time, right? And so quite often people go in and test the DNA in a river to see what's there, but they do it when it's convenient to them. So they go in the middle of the day and they take a scoop of water. Well, of course, middle of the day, the insects are asleep, the bats are asleep, the birds have all gone home. You know, the amount of DNA floating around right then is not high. Whereas if you leave it out 2 or 3 days, you're sampling so much of the water system coming down.
So if you get, we find out that there's a really nasty disease in this city.
Yep.
Can you then move upstream and test?
Totally. Yeah, we can find the source. Or imagine you've got a body. You know, someone's there's a body in here the police are trying to find. You can wander up looking for where the DNA, the human DNA, suddenly changes markedly. Although in an urban river, there's so much human DNA coming down that actually be a little bit more tricky. But yeah, totally. Say it was fire ants, right? And fire ants are particularly good because they use rivers to float around. Then you could detect the DNA and walk up the river looking for the tributary or the water source where that fire ant DNA is coming from. And so the test that we designed for the biosecurity species has fire ant DNA on it. So if you've got any fire ant DNA in that water, this test will set off an alarm And then because there's a big risk, industry often doesn't want to know quite exactly all of the diseases that might be in an area because it can cost a lot of money. And so the test really says, okay, you should look. You should really go and check here. We think something's going on before the alarms go off and huge economic costs. Go in and test this properly. But what we designed is a surveillance system that could monitor right across the country all nasty diseases.
So one of the other fascinating applications you described in the talk earlier was that you can have a look at the sediment to see what's the biodiversity now, and then you can like drill down the sediment.
Exactly.
What does that tell us about the past?
Yeah, so this is kind of an angle. My background is ancient DNA, and one of the things we worked out in ancient DNA, where DNA is preserved for a long period of time, is that sediments actually have quite a lot of genetic material in them from the past. And if you find a site where you've got layers of time, and that tends to happen around rivers, where when you have floods, and if you look at the cross section of a riverbank, you can often see the layers down, which are the former horizons of that dirt. We can go put a core down through that layered sediment record and actually then test at different points in time, and using the same genetic tests that we do for the water, exactly the same really, we can actually see which organisms were around at different points in the past. And that's kind of important because quite often we're trying to restore ecosystems or measure how much things have changed or gone wrong. If you don't actually know what it was like to start with, quite often it's difficult to tell how well you're doing or how bad the situation is or what's missing. And that's where using these sediments through time, I think, is a really important part of trying to restore an ecosystem or trying to measure changes in biodiversity due to temperature or human impact or whatever. The records are all there. It's just a technique of going back in time and finding them.
All right. Thank you very much for your time.
Thank you.
If you've got questions for Professor Cooper, put them in the comments and I'll forward them to him.
Brilliant. Thanks.
Bye.